All right, so far we've been looking at taking the radioactive, those unstable nuclei, and then seeing how they're going to naturally decay. So alpha decay, beta decay, positron emission, whatever it may be for that particular nuclei. And what we're going to see now is how we can kind of manufacture those similar types of reactions. So we're still going to be changing the element, so it's still going to be a nuclear reaction, but in this case, it's not going to be naturally decaying. In this case, with these transformations or these transmutations, this is going to be essentially taking that nucleus and bombarding it with some particle in order to cause a nuclear reaction to occur. And with it, if we're looking at a charged particle, especially if you think about like an alpha particle, for instance, or a proton even, in that case, it's going to be positive. So if we're trying to hit it against the nucleus, we're going to need that particle to be moving at a high speed. Otherwise, those positive charges from the particle, the positive charge from the nucleus are going to repel one another. So in order to achieve that, we've got these particle accelerators. You can see a picture here, and then typically, this is just, of course, a schematic. But with these sort of setups, we're pretty much always going to have them moving in a circle, just because the particle itself is going to be able to speed up more in a circle than it would in a linear path. But you can essentially just see here, we've got the particle. It's going to be moving around. It's going to be speeding up based on the charges there. So the charged particle, and then we're having another charge here to manufacture the movement, increase the speed of it, and then ultimately, whatever the target's going to be, that nucleus of that particular atom, is then just going to be hit by that extremely fast-moving particle and will kickstart a nuclear reaction. And with this is actually going to be the process that is used to produce every element above 92. So uranium is atomic number 92. That's going to be the heaviest naturally occurring element. So anything above that is going to occur via a process like this. And then with the elements above 92, this is a transformation or transmutation. So with the elements above 92, we just refer to them as transuranium elements, just because they're going to be coming from the reactions with uranium, essentially. And with this, we've got a couple different ways we can represent these equations. With the one we see here, this is just going to be the condensed version, and we're going to see how we can change this into the typical sort of format for a nuclear equation, where we have the reactants on the left, products on the right. But even just this format is still showing us those things. So what it's telling us here is we're going to be starting this reaction with aluminum 27, and ultimately we're going to be producing sodium 24. And then in that process, we're going to be starting the reaction with a neutron. So with the neutron itself, those don't necessarily need to go through the particle accelerator just because they're going to be neutral. There's going to be no repulsion between this neutron and the nucleus of the aluminum in this example. But with this, we're going to have these two kind of be our reactants, and we're going to have these two kind of be our products. So we're going to take a neutron and kind of just throw it at an aluminum nucleus, and then in that process, it's going to kick out an alpha particle and just leave us with this sodium atom. So if you want to practice kind of changing the reaction from this condensed formula into the sort of the typical format, just pause the video. Otherwise, I'm just going to kind of skip ahead to the actual equation itself. And we can see here, again, left-hand side showing us what we're starting with, and then what we're hitting that nucleus with. So in this case, N is just the neutron. And then the right half of this is what we're going to kick out of that nucleus, and then what's the major product going to be. And if we look at this equation, just like with the previous nuclear decay equations, we had the same mass on both sides. So in this case, we've got 28 and 28. We had the same for the atomic numbers on both sides. So in this case, 13 and 0, 11 and 2. So we still have 13. So we still have the balance there. It's just in this case, we're kind of having a particle kick off the reaction, and then we're also producing another particle. Whereas in the nuclear decay, we would either have like an alpha particle or a beta particle, positron being emitted. We could have an electron capture, but in the nuclear decay, we just didn't have particles on both sides like we do here. And then with this one, kind of a similar idea where we've got that condensed format, but in this case, we're trying to figure out what that missing piece is going to be. But we still have the mass needs to be balanced. We still have the atomic number needing to be balanced. So this is kind of similar to what we did with the nuclear decay. If we knew what we were starting with, we knew how it was decaying, we could figure out what those missing numbers were in terms of the atomic number, the atomic mass, and then look at our periodic table, ultimately identify what that new element's going to be. We can do something similar here. It's just now we've got two different particles involved again. So the neutron is what we're going to be bombarding this uranium atom with, and then we're going to kick out a beta particle. So we're going to essentially kick out an electron from that nucleus and then form some new product. So take a moment to see if you can kind of set that up and ultimately identify what X is representing in this nuclear reaction. And then with it again, just pause the video to give yourself a little bit more time if you'd like. But to set this one up, we can kind of, oops, I don't know why I have sodium there. Let me change that. So like I said, left-hand side of this is what we're starting with and what we're bombarding it with. So we've got that uranium atom, and then we're going to be hitting it with a neutron. So a mass of 1, atomic number of 0, just because it's going to be neutral. And then on the right-hand side, we're kicking out a beta particle. Beta particles, for our purposes, are just going to be massless. And then it's got a negative charge just because it's going to be that high energy electron. So we need to figure out what this missing piece is going to be. But again, the mass numbers on both sides need to be balanced. So on the left, we've got 238 and 1. So we know the mass here has to be 239, just because this beta particle isn't contributing to the mass. And then similarly with the atomic number, we need those to be balanced. But we've got 92 on the left, and then we've got a -1 for this beta particle, for this electron. So we're going to see the atomic number is just going to increase to 93. And then I, again, had sodium in there, which is not correct. But since we've got an atomic number of 93, we could look at our periodic table and see that it's going to be Neptunium. But again, with these nuclear reactions, we're always going to have the balance between mass and atomic number on the left versus the right. We'll ultimately see later on in the chapter, a small amount of mass is going to be lost in these nuclear reactions. That's why they're going to be producing so much energy. But when we're looking at the equations like we have here, we just want to make sure that we're balanced on both sides. So with the final one here, now we're kind of going in the opposite direction. Now we've got the entire nuclear equation. So we're taking a oxygen atom. An oxygen-16 is going to be extremely stable, 8 protons, 8 neutrons. But we're going to be then bombarding it with this hydrogen atom to kick out a alpha particle and ultimately just leave us with nitrogen-13. So see if you can then take this equation and kind of work backwards into getting this condensed format like we see here. And of course, in this case, we know what X is going to be. We know it's going to be the nitrogen atom here. And with this one, the very left-hand side of the condensed and the very right-hand side of the condensed notation are going to be relatively straightforward, because those are just going to be the atom, the large atom that we start with, the large atom that we finish with. And then what we put in the middle is just going to be those particles. So if we think about what we have with the helium atom on the right, again, that's just going to be the helium nucleus, I should say, is going to be the alpha particle. But then with this hydrogen atom, if we think about it, 1 proton, 0 neutrons, this hydrogen atom itself is just going to be that proton. So when we're looking at the middle of this condensed notation, we could put a P for the proton, and then we've got the alpha symbol for that helium nucleus. And then with this, like I said, the protons and the alpha particles, since they're going to be positively charged, in order for them to actually hit that nucleus, we need to have them accelerating. We need to have them at extremely high speeds. And in some cases, they also have different ions that they can use as the particles. So it's not always a proton, it's not always a alpha particle. But you can see here, this is just going to be a particle accelerator. So you can see this is going to be massive. I forget which one this one is in particular, but I know there is one in New York, so near where I'm from, although that one's on Long Island instead. But these are going to be so big just so that they have the ability to accelerate those particles to the necessary speeds. And then the scientists at these ones, depending on exactly what they're looking at, they're going to be looking at, of course, it's going to be different particles, different target material, depending on what they're looking at. But they're going to be examining the products of those reactions to see the high energy reactions that are produced with this. And like I mentioned, there's one in Long Island that I'm aware of. Cornell has one, I believe, in Ithaca, New York. And then the most famous one is going to be in Europe. So right on the border of France and Switzerland, there's the Large Hadron Collider. And that one's going to be massive. And it's actually, I think it's 100 meters underground, just to make sure that any of the radiation from space, so that cosmic radiation, if we think about the sun, for instance, the ultraviolet rays and things, so there's going to be radiation coming from space. So the Large Hadron Collider in Switzerland and France, right on the border there, is going to be 100 meters underground, just to make sure that any of the impacts of that cosmic radiation won't be affecting the results of their different experiments. And then with the Large Hadron Collider, that's a pretty impressive feat just of engineering in terms of building that. But also it's a good example of just how science works, because that's going to be a massive sort of institution that's going to have scientists from all over the globe, all different types of colleges and things doing different types of work just at that location.